Okay, Assalamualaikum and good evening to all my MEC281 material science students. Okay, so for this video, this is our third or fourth class. We are going to learn about the chapter 1.2 crystal structures, APF. APF stands for atomic atomic factor and density computation. Okay, let's go to the introduction of the crystal structure. Okay, the atom, the arrangement of atom in the form of either crystalline material or amorphous. Amorphous, or sometimes we call non-crystalline material. And then for the crystalline material, we have two types. One is the single crystal, only one type, and the other is the polycrystal, where it comprises of many single crystal or grain. Okay, so this is the arrangement of atom in the crystalline of the silicon oxide here. Okay, atom packed in periodic and 3D arrays, typical of the material that comes in the crystalline arrangement here. Commonly for the metals, many of them are ceramics and also some polymers. But for the non-crystalline or sometimes we call amorphous, tak teratur, not arranged, atoms have no periodic packing, occurs for complex structures and rapid cooling. Okay, this is non-crystalline silicon oxide, and this one is the crystalline silicon oxide. Even there are the same composition of elements, silicon and oxygen here, but if they are in the crystalline or non-crystalline formation, so maybe they have the different properties of the material properties. They maybe have different properties. Okay, so the structure of solid, let's say we see here the atom in amorphous are disordered, no recognizable or long range order. You cannot see the pattern between the atom here, but for the crystal you can see the pattern, because entire solid is made up of atoms in an orderly array, right, like this, and all atoms arranged on a common lattice. Lattice is the line of the 3D between the atom here. And the polycrystallines, where they are completely ordered, but they have different lattice orientation for each grains. So for the single crystal here, we only have one type of pattern, one type of grain. But for this, we have multiple grains that maybe they have different lattice orientation for each grain, for each different grain here. So that's why we call it polycrystalline. Okay, so for now, for the solid, you have to know three types. One is the amorphous or non-crystalline. The second one is the crystal or single crystal, and the third one is the polycrystalline. Okay, so that's the type of the structure in solid. Okay, so why we have to learn about the structures, crystalline structures of the solid? Because sometimes the material that we need for the specific applications, such as that in the turbine blades here, the single crystal turbine blades are able to operate at a higher working temperature than crystalline turbine blade. Okay, you see here the properties of the single crystal is much more beneficial to the applications here compared than to the crystalline. Okay, we have a break for 5 minutes. Okay, test. Okay. Okay, where were we? Okay. Okay, and then for the turbine blade, we need the properties in the single crystal that give much better compared to the crystalline turbine blades. Okay, because they are able to increase the thermal efficiency of the gas turbine cycle. Okay, that's why we have to learn the properties of the structure in the solids, whether it is the amorphous, crystal, and or polycrystalline, so that they may have different properties, and that particular properties we need to the certain applications, okay, in the engineering applications. Okay, so let's go to the next slide. Okay, most engineering materials are polycrystal. Okay, this is just the diagram of let's say here we have the unit cell directions. Okay, in the multiple green for the multicrystalline. So this is the polycrystalline material. They have many grains, and for each different grain here, they may have different direction, cell direction like this. Okay. Okay, so now you can ask yourself. You can try to explain what is the crystalline materials, amorphous materials, single crystalline, and the polycrystalline. So you can try to sketch the formation of the crystalline, amorphous, single crystalline, polycrystalline formations. Okay, so let's go to the crystal structure. Okay, so this one is the lattice and this one is the motif. So if we combine between the lattice and motif here, and then we will have the crystal structure here. Okay, crystal structure. So what is the lattice? Lattice is the line network in 3D. Okay, let's see here. So this one between the 3D here is the lattice. Okay, and then the motif is atom are arranged in a repeated pattern. So this is the general formation structure where we unit cell here plus the lattice, and then we will have a crystal, a three-dimensional or 3D repeating array. Okay, so that's what we call a crystal. Okay, so you can try to understand on these diagrams. Okay, so let's go to the Bravais lattice. Okay, this is the crystallography based on the diagram. Okay, geometric diagram. Okay, describe the Bravais lattice itself is describing the geometric arrangement of the lattice point and the translational symmetry of the crystal. So there are different types of the geometric arrangement. Okay, they may become in the isometric equal faces, or maybe they are in the rhombohedral, tetragonal, and so on. So they may be in the form of primitive, body-centered, face-centered, or base-centered. Okay, there are difference of geometry arrangement. Okay, so let's see the crystal system here. There are 7 in the list here. There are 7 types of crystal, and then the dimensions and angles are different for each type of crystal system, and the Bravais lattice also a difference. Okay, so this is the general knowledge for you. Okay, this is what we are going to go deeper. The crystal structure of metal. Okay, common crystal structure for metals. We have three types. One is the AC. AC stands for the simple cube. Simple cube, like a regular cube. And then we have the BCC, or we call body centered cubic. So difference between BCC and AC, there is an atom in the center, so that's why we call it body centered. So there is one more atom in the center of the other atom of the corner here. So there is one in the center, at the center. Okay, so the third type is what we call FCC, face centered cubic. So there are another face here, 1, 2, 3, 4, 5. So okay, compared to this diagram between SC, BCC and FCC, okay, at the first glimpse I will see that the FCC is more compact, right? Because it has more atoms compared to BCC and SC. So the SC is the least compact, the least density here. Okay, so this is what it looked like for the simple cubic. There is no atom at the center. Okay, so this is the BCC, so there will another atom in the center, body centered cubic. And then this is the FCC, so there is the face, half of the atom at the face, at the center face of each what we call each face lah. Okay, so atoms are located for the FCC here. Atoms are located at each of the corners and the center of all the cube face. Each corner atom is shared among 8 unit cell. Face-centered atom belong to 2. Okay, bentuk macam ni lah. Jadi, nak senangnya awak kena cuba lukis dan ingat. Okay, sebab mungkin ini ditanya dalam quiz, dalam test. Kita tak tahulah. Okay, sebab ni awak kena hanya lukis dan hafal. You have to memorize while you make a draw, a sketch of the FCC, BCC and SC. Okay, simple ya kan? Awak start dengan SC dulu, lepas tu awak tambah satu kat tengah, tu jadi BCC, and then awak buang kat tengah, awak tambah separuh dan separuh kat bawah. So ni what we call the FCC. Okay, so tu jenis-jenis types of the cubic structure, the crystal structure in the metals. Okay, let's see again. Manganese, the common elements found in the SC. Alpha iron, chromium, molybdenum, tantalum, tungsten and vanadium are BCC, and the gamma iron, aluminium, copper, nickel, lead, silver, gold and platinum are FCC. So don't worry about that. You can see in the list of the table in the where is my table here? Okay, here. Okay, this one I obtained from the book at material science textbook, your textbook. If you do not have that textbook, you can Google it, or Google it to get the list of the metals and its crystal structure and also their atomic radius. Okay, but if the question is asked in the quiz or test, the atomic radius will be given in the question, so you do not need to memorize all these informations. Just when you have to design or where you have to study, you can refer back in the textbook or find the information in the internet. Okay, so let's go to the next topic. what we call the atomic packing factor. Okay, this is the simple calculation based topic. Okay, APF, atomic packing factor, is defined as the efficiency of atomic arrangement in a unit cell. It is used to determine the most dense arrangement of atoms. Okay, it is because how the atoms are arranged determine the properties of the particular crystal. In APF, atoms are extremely closely packed and are treated as hard spheres. It is represented mathematically by the number of atoms. Okay, this is how many atoms times the volume of atom in a unit cell, the symbol of Vs, per the volume of unit cell, Vc. Okay, so from the value of APF, we can predict the properties of that elements. Okay, because we know if they have high APF factor, so maybe it is more brittle and more hard lah. Okay, so this is the calculations how they derive APF formula for the SC. Okay, and this exercise is to calculate the BCC and FCC, the APF, but finally we have the equation here for each SC, BCC and FCC. Okay, so let's try these equations here. If atomic radius of aluminum is 0.143 nanometer, okay, if the question is not giving the value of radius, you can find in the table here, but since it is given in the question, so you have to use the value here, 0.143 nanometer. Calculate the volume of its unit cell in cubic meter. So the question wants you to find the volume of its unit cell. Okay, so how to calculate this? Okay, we have to know that the structure itself, what is the crystal structure for the aluminum. Okay, aluminum here is the FCC, so the equation for the FCC here is 4 times 2 times R to square root of 2. So you have, okay, wait a second, we have a break. Okay, anak kacau. Kita sambung balik. Okay, untuk FCC, equation dia adalah VC equal to A to the power of 3. A equal to this one. So 2R square root of 2 power of 3. So you will get here 16R the power of 3 Okay. Okay, so you substitute the R is 0.143. R means for the atomic radius. So this is about the aluminum. So you have to take the value of aluminum radius 0.143 here, and then power of 3 times the square root of 2. So you will get the value here. This is the volume unit cell VC. Okay, volume of unit cell. Volume of unit cell. Okay. And now you can try the tutorial 3. Okay, I will put later in the Google Classroom the tutorial. So you have to do by your own. You have to do the exercise, and then if you have the problems to understand or the problem in solving the question, you can ask me in our WhatsApp group. Okay, so let's go to the density computation. Okay, knowledge of the crystal structure of a metallic solid permits computation of its density through the relationship. Okay, yang tadi kita kira APF, atom packing factor. Okay, sekarang ni kita nak cari density. Density apa? Okay, density bagi structure tu sendiri. Okay, so rumus dia adalah density equal to n. N is the number of atom associated with each unit cell. Okay, A is the atomic weight. This is the value you can find in the periodic table. VC here is the volume in your unit cell. That one that we have already calculated here using these equations. Okay, this equation also is different based on the type of the cubic, whether it is SC, BCC or FCC. Okay, and let's go back to the density here. And then NA is the Avogadro number. So this is the constant of Avogadro number. As we know, it is the value of 6.023 times 10 to the power of 23 atom. This is the constant value, so it is fixed value. Okay, and then that's it. That is the equation how to calculate the density. Okay, let's try this example. Okay, iron has BCC crystal structure. So you know now, iron has BCC. So an atomic radius of 0.124. So you know it is BCC and its R is 0.124 Newton meter. An atomic weight of A is 55.85 gram per mole. Compute and compare its theoretical density with the experimental value found inside the front cover. Okay, the front cover here means that if you have the textbooks, you have the properties of every element in the front cover. So you have to compare the value that we calculate here with the experimental value in the front cover. Okay, never mind. So let's try the simple equation here. Density equal to Na. Yeah, this one. Density equal to N A atomic weight over volume of unit cell times N A, and A Avogadro number. Okay, so here for BCC, N equal to 2 atom per unit cell. How do you know the value of N equal to 2? Okay, this is what we discussed here. BCC has 2 atoms per unit cell. FCC has 4. Simple cubic has 1. Okay. So the equation for the unit cell volume for the BCC is here. Okay. So you have to find the VCC first, or you can also substitute the VC into this equation straight away. Okay, never mind, we try to calculate by our own. Okay, we find the VC first. 4 times R. R is 0. Yeah, is 1. 0.124. Okay. Over the power of 3. All the power of 3. Okay. Uh, 4 times 0.124 over square root of 3. Okay, so I get 0.02348. Okay, what is the unit of here? Okay, so it is Newton meter cube. Okay, so never mind, we can leave it as the unit of unit cell per unit cell. Nano. The prefix for nano is 10 to the power of minus 9. Okay, so we have a confused value here. Okay, so in the meter, so we have, what is the value here? Okay, meter, nanometer, and then it convert into the cm, so that's why it has the value of 10 to the power of minus 7 in the cm. Okay, let's say I want to maintain here in the meter, so at the end of the value we will get the value of gram per meter cube. Okay, and so on lah. And then the Avogadro number here, just substitute the constant value of Avogadro number, which is 6.022 times 10 to the power of 23 of atoms. And then finally you will get the value of 7.9 gram per centimeter cube. So this is the value of density, okay, mass per volume, right? Density, as we know, mass over volume. So here is mass, the unit of mass, and the centimeter cube here is the unit of volume. So it obeys the law of the density. So when you compare the value, it is not a far value compared to the experimental value. Okay, so it is considered correct. Okay, so that is the calculation how to calculate the density. So to find the density, you have to know the unit cell volume here, VC. How to calculate the VC volume, you must determine first either the structure, crystal structure, that it is BCC or FCC or also SC. So based on that, we can know the atom, how many atoms in the unit cell. Okay, so let's try the other exercise. Okay, and then let me know if you have the problems. Okay, you can check the value in the internet. If it is similar value, so it sounds correct. Okay, I think that's all for this subtopic, crystal structure. And don't forget to do the tutorial for the crystal structure. If you have the problems, let me know, ask me in the WhatsApp group. Okay, I think that's all. So the next class, we are going to learn about the 1.3 crystallographic point direction and planes. Okay, so I put this subpaper in the other video. So for this video, we just end here, and good luck for your exercises and tutorial. Okay, Assalamualaikum and good evening. Salam sejahtera. Okay, bye.